This is just going to be another proof for the conservation of momentum formula. Let's say we have a small ball, just like we did before, of mass m1 going at a constant velocity u1, and we've got a larger ball here of mass m2 traveling at a constant velocity u2. And let's say these balls are on a collision course with each other, and we want to analyze what happens when they actually end up colliding, what are the forces they exert on each other, and as a result, is there a conservation of momentum? Well, when they do actually collide, assuming that they do collide, we can draw a free body diagram describing the forces they exert on each other. So, and don't forget that while they are colliding, there is a small time period where they will actually be in contact with each other. It's not an instantaneous thing. They will be in contact with each other for a certain amount of time. In fact, you can imagine they'll be compressing each other a little bit, sound waves, heat will be exerted, whatnot. But the important thing is that there is a time, delta t, in which they do end up colliding with each other. And not only that, but the forces they exert on each other will change over time too. But let's not rush ourselves. Let's say there's a force that's being exerted on the small ball due to the large ball, F2, and there's a force being exerted on the large ball by the small ball, which I'll call F1, right? And this force changes with time, right? I mean, as they're compressing each other, the forces that they're exerting on each other may change, right? I mean, imagine once they're midway through their compression, this larger ball could be a little bit more compressed and will be exerting a larger force back on the small ball, right? So it would be a mistake of us to assume that their force remains constant. And to demonstrate that, let me just draw you a rough idea what I think would be an appropriate generic graph describing the force 2 with respect to time while they're colliding with each other. So if time was on the x-axis and force 2 was on the y-axis, right? And let's start our time axis at 0 before they collide, like maybe just here in this particular case. And let's denote ti, the moment where they do actually start colliding, right? Based off your intuition, you'll probably be able to tell me that there will be no force being exerted on the small ball due to the large ball the second they touch, but when they do end up compressing each other more, the force gets greater and greater. And just before they leave contact with each other, the force will diminish back to 0 just before they finally stop touching each other, and that will be TF. So to summarize, TI denotes when the two balls come in contact with each other, and TF denotes the time when the two balls finish in contact with each other and start moving off in their separate velocities. So, if we were to draw a free body diagram for, say, the small ball right here, I'll write this here, small. If we were to draw a free body diagram for the small ball just here, there's only going to be one net force acting on this ball, and that's just going to be F2 due to the larger ball, right? And not only that, but the smaller ball has a mass m1 like we discussed before. So if we were to do our dynamics equation, we know that the mass of our small ball times by its acceleration at a particular point is going to be equal to the net forces acting on that particular ball, which in this case is simply just going to be m1 times a1 is going to be equal to f2. Right? There's only one net force acting on this ball, and that's just F2. I could have written F2 minus 0 if I like, because there's no force in this direction, but I've skipped that step. Right? Let's analyze what A actually means. Remember, A is the instantaneous acceleration of our object at any point while these two balls are colliding with each other. Right? The best way to measure instantaneous acceleration is through calculus. m1 times dv dt, right? V denotes the velocity of this ball sometime, anytime at t during the collision, right? And F2 is this one. So for example, this t could be right here during the collision, and it's got a particular velocity. And this V1 denotes that velocity, right? Let's now do a free body diagram for the large ball and see what we get. Well, just like before, there's going to be only one force being exerted on it, and that's due to the small one, F1, right here. Well, we know from our dynamics equation that M2 and don't forget that the larger ball has a mass m2 times by its acceleration at some particular point. In fact, I could probably even write this as a function of time if you like. A of t, I could have done it over here, is going to be equal to the net forces acting on it. Right? Actually, net forces acting on it, it's just 1. Yep. And then if I were to re-expand this, it would be m2 times by, just like we did before, dv to, it's obviously that it's a function of time, dt is going to be equal to F1, right? Because the only external force acting on this ball is F1. And don't forget that V, in this case, V2, denotes the velocity of our second ball at some point during the collision, right? I really want to make this seem as arbitrary as possible because that's exactly what it is. This V denotes any point during the collision, right? It doesn't have to be initial, doesn't have to be final, any point, right? So these are two very useful equations we've got right here. This one and this one. But there seems no easy way to equate them. But just like we did in the last video, we know there is a way we can equate them using Newton's third law. We know that each action has an equal and opposite reaction, and in this particular case, even though these forces are varying with time, they will always be equal and opposite to each other. So we know that F1, make that a little bit clearer, we know that F1, the vector F1, even though it's changing, is always going to be equal to the opposite of F2, right? Let's sub all of these formulas into our third law and see what we get. Well, if we were to plug F1 in the left-hand side, we'll get m2 dv to dt is going to be equal to negative m1 dv1 dt, right? And if I were to group this all on the left-hand side, I can write m1 dv1 dt plus m2 dv2 dt is all going to be equal to your zero vector right here. Excuse my handwriting. Not only that, but because m1 remains constant and it's a scalar, we can easily group this inside the differential equation, right? So we can say that this term right here is the exact same as saying d dt of m1 v1, right? Remember, if it's a constant, you can just easily bring it outside of the differential sign. Not only that, but you can do it for the second term as well. d dt of m2 v2 is going to be equal to your zero vector right here. Let's analyze this a little bit further. Remember that differentiation is accumulative, right? So if you want to differentiate the entire left-hand side, that's the same thing as differentiating each of the individual terms. So you can do that in reverse too. This is the exact same thing as differentiating the entire thing altogether. d dt of m1 v1 plus m2 v2 is going to be equal to your zero vector. Right. Let's analyze this a little bit further and integrate with respect to time. If we were to integrate with respect to time, we could just write m1 v1 plus m2 v2. Remember, v1 and v2 just denote their velocities of the first ball and second ball at some time during the collision, right? And that's going to be equal to the integral of your zero vector with respect to time from your initial collision point to your ending collision point in time. So it's going to be your final point, your initial point where they started colliding, and all the way to your final point where they started colliding. We'll see how important that becomes later on. And the right-hand side, if we're analyzing, remember, if you were to integrate 0, you just get left with a constant, right? Because in reverse, if you were to differentiate a constant, you'll be left with 0. So this just becomes a constant vector. It's just a 3-element vector with nothing but pure constants inside. And on your left-hand side, nothing's changed. You still got your mass of your small ball times by its velocity. sometime during collision plus m2 times by its velocity sometime during collision 2. And this is going to be equal to a constant. Let's describe what this means now, because we've actually solved the problem, but let's discuss what this means by this formula so we can actually see if we can prove the conservation of momentum. Well, if we know that actually, let me re-expand this. We know that by definition, momentum is mass times velocity. So this will be your momentum of your small ball sometime during your collision. And we know this is your momentum of your large ball sometime during collision. And that's going to be equal to your constant vector right here. Don't forget momentum is also a vector, right? Let's analyze exactly what this means. If we're given a sum of all your momentum of your first and second ball at any time during the collision from start to finish, from start when they start colliding to the time they finish colliding, and that's always going to be equal to a constant, that means we can say at any particular point all of momentum of the first and second ball is going to be the same. So we can, just using your intuition here, imagine that all the momentum at any particular point is going to be equal to a constant, right? That means we can say that means the instant that they start colliding with each other, so I'll put that as P1I, denoting the momentum of the first ball when they start colliding with each other, plus the momentum of the second ball when they start colliding with each other, is going to be equal to the momentum of the first ball when it finishes colliding, plus the momentum of the second ball when it finishes colliding, right? This is quite a big step here, but I hope you can understand what I'm saying here. If all the momentum in one particular system at any point in time is constant, that means that the total sum of momentum from start is going to be equal to the total sum of momentum as soon as they finish. And there we go. This is the conservation of momentum formula. It basically shows that the sum of momentum before collision is going to be equal to the sum of momentum after the collision, right? And that's the proof just there. I mean, that is a proof in itself, right? It means that momentum has been conserved from start to finish. And there we have it. That's a calculus proof for it. I hope that makes sense.